So in section 10.6, we're going to shift our focus away from polygons and instead focus on circles and parts of circles that we call arcs. So getting into this vocab section, we can see that in a plane, a circle is what we call all points that are equidistant from a given point called the center. Again, equidistant meaning the same distance from the center. A diameter is a segment that contains the center of the circle and has both endpoints on the circle. And that means a radius is going to be a segment that has one endpoint on the center and one endpoint on the circle. So if I have a diameter going straight across, so something like AB would be a diameter from one side of the circle to the other, going through the center, which is at P. Just going from the center to the edge, again, we're just going to call that a radius. So something like segment PC would be a radius. Congruent circles would have congruent radii, and a central angle is an angle whose vertex is the center of the circle. So something like angle APC we could describe as a central angle. They have that little measurement in there for it. We also name a circle by its center, so the circle that we have below, the circle has a center of P. We just use that symbol for it. It's a circle with a little dot in the middle for the center. Call that circle P. And we can use the circle to find any length of the part of a circle's circumference, as long as you relate it to an angle that's inside the circle. So what we refer to as an arc is just part of a circle. And one type of arc, a semicircle, is if I go halfway around it, so half of a circle. So looking back at that last question, I could have a semicircle as long as I connect points A and B. So a minor arc is going to be smaller than a semicircle, so you just want to think less than halfway around. Something like from A to C would be a minor arc, and a major arc would be larger than a semicircle. So we could make a major arc in that last example by starting from A, but then going a long way around to C because it's bigger than a semicircle. So we're going to name a minor arc by its endpoints and a major arc, or a semicircle, by its endpoints, but also another point on the arc. So we're going to see that when you name a major arc, we have 3 letters for the name. So STR, for example, would be the major arc that starts at S, passes through T, and ends at R. And if I name a minor arc, that's just going to have 2 parts of that name, just going between R and S. If we just use 2 letters for the name, we assume it's the shortest distance between those 2. So we can see that RS is a minor arc, it's less than halfway around. STR is a major arc because you're going more than halfway around your circle. And the reasoning for the name, again, STR just means that we have to pass through T in order to get to R. If I just say RS, again, we just assume that it's a shorter distance, so that's why it's less than halfway. So if we take this next example and try to name some minor arcs in this circle, so this would be circle O. AD would be an example of a minor arc. Again, that's our short distance that's less than halfway around. Could also use DE that's next to it, also less than half a circle. E to C would be a minor arc, and also C to A would be a minor arc for the same reasons. Something we could do is we could reverse the names. If I said AC or CA, it's referring to the same minor arc, so we do have to find 4 distinct arcs. Could reverse the names though. So when I said arc DE, could have also referred to that as arc ED, same as the name that I reverse it. If we look for the semicircles, again, semicircle is exactly halfway across, so it looks like I have 2 diameters, segment AE and segment DC. So there's actually 4 semicircles that we could make with those 2 diameters. I could start at A, pass through C, and end up at E on the other side, so that would be 1 semicircle. And I could use those same 2 endpoints, A and E, but instead pass through D. That would be a separate semicircle. That's why we use 3 letters for the name. ACE describes one half of the circle, while ADE describes the other half. And I could also shift that to the other diameter. If I say DAC, that would be yet another semicircle. And again, going from D to C, I could pass through E instead, and that would be my 4th semicircle. DAC, again, covers the top half, and DEC would be a semicircle on the bottom half. So now if we want to look for major arcs, again, we're also asked that it contains point A. We should just look for any segments that any arcs that pass more than halfway around your circle. So one that I found was CAE. Again, if I just use the name CE, we would refer to the shorter distance, so that would be a minor arc. If I include A in the name, CAE, that makes sure I pass through A on my way to E, so that's going to be the long distance around the circle. That makes that a major arc. Something else about that name, CAE, is that we could call the same major arc CDE, because it passes through that point as well. It's not going to change the actual arc itself. So I could call that CAE or arc CDE. Either way, it's referring to the same thing. Different arcs that we could make, though, is something like EAD. Again, more than halfway around your circle, and it passes through A. Don't want to just say ED, because that would be a minor arc. We could use a major arc that's DCA. So now I'm connecting these two endpoints at D and A, passing the long way around through C. And just like that last name, we could also name this DEA because it passes through E as well. And one more major arc that we could name is ADC. So it contains point A because A is an endpoint. If I go from A to C again, that's more than halfway around your circle. As long as I'm not going the short distance, which would be a minor arc. So one thing that we can do with arcs also is find their measure. Measure of a minor arc is going to be the same as the measure of the corresponding central angle. So in this case, if I have a 50-degree angle listed in the center of my circle, if I'm looking for the measure of that arc RT, which looks like a minor arc because it's using 2 letters for the name, that's going to be the same as the angle, so that's just going to be 50 as an arc measure. If I want to find a major arc, though, I can find the measure of the related minor arc and take that away from the circle, so I'm subtracting that from 360. So for example, if I want to find the major arc for TQR, so now I'm not going the short distance between T and R, going the long way around, I can just take the rest of the circle, would be 360, take out the 50 degrees we already found, and that tells us that 310 degrees is left for that major arc. Nice thing about semicircles is it's always half a circle, so the measure of a semicircle is always going to be the same thing. It's always going to be 180. Other definition to come up with is that adjacent arcs are arcs of the same circle that have exactly 1 point in common. And we can add the measures of adjacent arcs just like we can add adjacent angles. So it's a pretty similar concept to when we last saw adjacent angles. Adjacent arcs, you just want to think of as right next to each other. And if I want to find the combined distance of, let's say, a measure of arc ABC, and this looks like it would be a semicircle, even though we're not sure, because we're not sure if that's a diameter. If I want to find the measure of that combined arc that passes from A through B on its way to C, I could take the 2 adjacent arcs and add them together. So I can find the measure of arc AB, add the measure of arc BC, and that would give us a total from A all the way to C. So say if this was 40 degrees plus 140 degrees, I would have 180 total. So trying that in the next example, first case we just have a minor arc, I just have BC. So in that example from up above, that's just going to be the same as our central angle. 32 degrees in the middle means it's going to be 32 degrees on the outside of our figure as well. So first answer we just get a straightforward 32. Next example is where we have our first adjacent arcs that we're adding together. If I'm trying to find the measure of BD, that's still a minor arc, but I can take the 2 arcs that are making up BD, which is BC and CD, and just add those together. So all we're doing is adding the 32 plus the 58. That's where we get 90 degrees for the measure of arc BD. Also looks like a right angle in the middle, so that's how I can verify that should end up as a 90. And arc ABC looks like it's again describing a semicircle because AC looks like a diameter passing through the center. So anytime I have a semicircle, I can just straightforward give a 180 as an answer. It's always going to be the same thing. So ABC, that semicircle is always 180. And I can then use that to find the last answer. If I'm just looking for the measure of AB, that arc towards the bottom, I can start from the semicircle, so I can start with 180 and just subtract the 32 that's left. Because if I take away this small piece of the arc from B to C, I'm left with what we're trying to find, which is the distance from B to A, or the measure, sorry, from B to A. And if I take that 180 and subtract my 32, I'm left with 148. And again, that would be in terms of degrees. So we also have circumference of a circle. Circumference is the distance around it, so kind of like a perimeter and a polygon. And the number pi comes from the ratio, not ration, of the circumference of a circle to its diameter, which is really how pi, you can write it out as a fraction. Never really going to have to find pi itself, though. We can always use that in our work. When we're trying to find circumference, though, that's always going to be either pi times diameter, or we could also use the radius. That would just be 2 pi times the radius. Again, just from the fact that a diameter is twice as big as a radius, both of those formulas are basically the same, just using different pieces. Another definition is that coplanar circles that have the same center are going to be concentric circles. So concentric circles you want to think of as something like this next question. So the description goes into up above, but it says basically you have 2 rails for your track. We're trying to film this actor and we have a track around him. We have a rail for the outer edge, and we also have a rail for the inner edge of the circle. So what we want to find is how much further does a wheel on the outside edge travel compared to a wheel on the inside edge, which really means we're trying to find the circumference of these 2 concentric circles. And again, that's circles that just have the same center. They both have the center where that actor is standing. So in order to find this distance, again, we're going to have to find the difference between the big circumference and the small circumference. If I take the outside wheel minus the inside wheel, that tells us the difference in how much further we travel. So for the big wheel, again, we can use 2 pi times a radius. We don't start with a diameter. Instead, we start with just a length given from the center to the edge. So the radius of the big circle is just going to be a 10. And if I substitute 10 in for the radius, again, that was 8 plus 2, I find that the circumference of the bigger circle was 20 pi. We can leave our answer in terms of pi because, that's always just going to be a constant for that pi. And for small circle, all we got to do is find that smaller radius as 8. And again, same formula. Circumference is 2 pi times the radius. And now that I know that the small circumference is 16 pi, to find the distance that I travel on the outside compared to the inside track, I take 20 pi minus 16 pi. I can just subtract the coefficients and leave my answer in terms of pi. That would just be 4 pi. And that's all given in feet. So again, just looking for the difference in those two circumferences. And all we got to do is substitute in the radius that we find. So last part of this, is to look at what we call an arc length. Because the measure of an arc that we've been using before is in terms of degrees. But if we want to find arc length, we have to find what fraction it's going to make out of the total circle's circumference. So it seems like kind of a complex formula. We have that the length of an arc is going to be the measure of the arc divided by 360 times the circumference, which again we can either put as 2 pi r or pi times diameter. So the beginning of this formula looks kind of scary. You got m with arc AB divided by 360. All you're really looking for, though, is what fraction does your arc make from the circle. And we'll look at that in practice on the next couple. If I use the formula, if we're trying to find the measure of the arc length from x to y, first thing we can start with is the measure of the arc in terms of degrees. Since you use a right angle as your central angle, the degree for the arc would be the same. It would also be a 90. And we'll also start with the fact that the diameter of the circle is a 16. We need both parts for the formula. So again, the arc length, all we're doing is we're looking at what fraction of the circle do we have for that arc, and multiply that times the circumference. And the fraction of the circle is just 90 degrees out of 360, which we can simplify and just think of that as 1/4. Because again, this arc is basically just 1/4 of the circle. And then if we just take that last answer for a fraction and multiply by the circumference, again, if we start with diameter, it's just 16 pi for the circumference. If I multiply that by 1/4, I'm just left with 4 pi as the length of that arc. Same kind of question on B. All I got to do is figure out if I'm measuring this arc, and this looks like a major arc, xpy. I just need to know what fraction of the circle this arc makes and multiply that by the circumference. So this time we start with 240 listed as the measure of that arc in terms of degrees. And we also start this time with a radius instead of a diameter. So I just listed those both to start. Again, same formula. I just look at that as a fraction. 240 out of my entire circle would be 240 out of 360, which means that the arc in terms of a fraction is 2/3 of our circle. And if I substitute my radius into the circumference formula, 2 pi times the radius comes out to 30 pi. So last step, just like the previous problem, is take 2/3 times that 30 pi, and we end up with 20 pi as an arc length. So again, kind of a complex formula. Big idea there is just look at what fraction does your arc make out of that whole circle. That second arc was 2/3 of the circle, but our first arc was 1/4. Just take that answer and multiply by circumference, then you have arc length.